Welcome back to our ongoing look at complex numbers being turned into polar coordinates. Well, not technically polar coordinates because that's strictly for rectangular, but we can find a polar analog. We can find a polar form of complex numbers. And so last time we looked at how to do that, and all this was motivated by a pretty simple sounding question that we still haven't gotten an answer to. I mean, I gave you the answer, but we don't know how to get to that answer. So what we're going to do today, or whenever you choose to watch this video, is answer that question. So here's where we left off, finding polar forms of complex numbers, right? You can have any complex number, a plus bi, and you can get from there to a polar analog, a polar form on the complex plane, by r cosine theta plus I sine theta, where r is your modulus, your distance from the origin, your absolute value, which is just the square root of the sum of the squares of your a and b, your real and imaginary parts. And then theta satisfies the equation, right? Tangent theta is opposite over adjacent, b over a. But you also have to do a little work. You have to modify it to get into the appropriate quadrant, because if you just took the arctangent of b over a, you would get only values sitting in the first or fourth quadrants. Arctangent does not give you any angles in the second or third, so if your point is in the second or third, you kind of have to adjust accordingly. But that is where we were. We were able to take any point, convert it into a complex or a polar equivalent. There we go. So, I ask again, what is the square root of I? Well, first thing I want to do, because I can't do that straight up, right? I can't just take the square root of I and get the root 2 over 2 plus root 2 over I thing I had before. So what I have to do is start with a polar form and take the square root of that. So the polar form of I, the polar form of 0 plus 1I is going to have radius 1, and tangent is 1 over 0. It's undefined. So rather than panic, let's just stop and think, when is tangent undefined? Well, it's at 90 degrees or 270, right? You're either straight up or straight down. And since 1i is straight up, theta has to be pi over 2. So r is 1, theta is pi over 2. So this is my polar form. I, which is what we started with, is actually equal to 1 onto cosine of pi over 2 plus I sine of pi over 2. All right. Well, let's go for it. Let's pull that trigger. If I want to take the square root of I can equivalently take the square root of r cosine theta plus I sine theta. And since r is always positive, right, absolute value is always positive, I can pull it out of this single radicand and make it be its own radicand. Because it's always positive, I can do that. And then I just have to contend with the square root of cosine theta plus I sine theta. Because the square root of r is just a real number. For this one, right, the square root of 1 is just 1, so that's okay. We really have to deal with this now. And so I think I've put this off for far too long. We need to get to it. So here we go. What is the square root of cosine theta plus I sine theta? And here is where I work in the claim from the original video in general. I tell you that cosine theta plus I sine theta, if you were to take the square root of that, you would actually just halve your angle of rotation. That's all that would happen. So cosine theta plus I sine theta becomes cosine theta over 2 plus I sine theta over 2. And I want to prove this to you because this will bring in some of the identities we've been looking at so far in these recent weeks. Right? You square out this thing, then you've got first term squared, that's cosine squared theta over 2. You've got last term squared, which is I squared sine squared theta over 2, and then 2 times the product of each term together. Right? That's squaring out a binomial. That's pure algebra. And so I've got cosine squared theta over 2, 2i cosine theta over 2 sine theta over 2, and plus I squared sine squared theta over 2, which is a bit of a mouthful, I'll admit, but I've got cosine squared theta over 2. And then I'm going to take this guy, recognizing that I squared is negative 1, and combine all my real parts, right? This is a real number for all values theta, this is a real number for all values theta. So I've got cosine squared theta over 2 minus sine squared theta over 2. And then I just have this imaginary piece left over, 2i cosine theta over 2 sine theta over 2. Now wait a minute. Didn't we have an identity that dealt with cosine theta angle minus sine squared angle? And indeed we did. We had a double angle for cosine equaled cosine squared angle minus sine squared angle. So this simplifies down to be cosine of the double angle, double theta over 2 cosine theta. And over here I've got 2 sine theta cosine theta. Why that? Is a double angle for sine. So the 2, the cosine theta over 2, the sine theta over 2, all that just becomes sine theta. So would you look at that? Cosine theta over 2, I sine theta over 2, that squares out to be cosine theta plus I sine theta. Or in other words, the square root of cosine theta plus I sine theta is cosine theta over 2 plus I sine theta over 2. We got it. That's it. That's perfect. So finally, the root of I, the square root of 1 onto cosine pi over 2 plus I sine pi over 2 becomes 1, right? The square root of 1 is just 1, times cosine pi over 4 plus I sine of pi over 4. And cosine of pi over 4 and sine of pi over 4 are each root 2 over 2. So if I were to go back into a plus bi form, I would have root 2 over 2 plus root 2 over 2i. And that's it. That's got it. Now, there is another result from this, right? This was just for square roots. And before I really intimidate you, I want you to look at this, right? So when I raised cosine theta plus I sine theta to the 1/2 power, I ended up halving my angles. And the theory came about, or the question came about, well, if I raise this expression to any exponent I want, am I just going to be ending up multiplying these angles in here by that same exponent? And the answer is yes. A theorem that I'm not really going to prove in this class because it's asking for just a little too much. I can do it for integers, I can do it for rational numbers, but I can't do it for all real numbers. Sorry to say. But there is a theorem. I'm going to call this de Moivre's. I don't actually know how to say that name. But he was the one who proved once and for all that yes, you raise any complex number to a power. That's the same as taking the polar form raised to a power, and each of those r's raised to that power, so that's easy to compute. And the angles, you just multiply by the exponent. And I'm not going to prove that. I'm not going to, because the best proofs of that for all real numbers, k, requires the use of Euler's identity, which, by the way, is a head-exploding thing. Cosine theta plus I sine theta is actually equal to the natural exponential e to the I theta. I'm raising e to a complex power, and that's equivalent to cosine theta plus I sine theta. That's equivalent to the angle of rotation of a complex number. I'll let that sink in for a minute. Also, for those of you wondering, this is why e to the I pi equals cosine pi plus I sine pi, which equals -1. E to the I pi equals -1 because of this identity right here. And that's really, unfortunately, all I can get into it, because proving this thing is well outside our reach. We are way out of our depth if we're going to try and prove this one. But I just brought it up because it's nice. And actually, if you buy into it, if you believe it, then proving de Moivre's theorem actually is pretty straightforward, right? This polar form turns into r e to the I theta. Exponent rules ensue. And yeah, de Moivre's falls right into place. But I'm not going to do that. And also, just believing theorems because they're presented to you is a profoundly unmathematical thing. So I totally want you to all go far enough in your math careers to where you can actually see the proof of this and appreciate it. That's not today, though. We're pretty much out of time for this video, so I will see you next time, and we will finally start to exult in our results. We will finally use the results we found, de Moivre's, maybe incorporate some others, and actually do a whole bunch of complex arithmetic. So I'll see you then.